Okay? And there, look at this. Look at all the buzzwords that you can hear about if you just pick up, or listen to what's going on in machine learning. You've got GANs, generative adversarial networks, you've got random forests, you've got deep learning, you've got, bagging Bayesian algorithms, you've got reinforcement learning, collaborative filtering, blah, 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 Gaussian processes, this, that, and the other, transfer learning, logistic regression, Boltzmann machines, and so on and so forth. I mean, clustering. I mean, look at this. It's just a complete jungle, a complete zoo of buzzwords. Okay. So I thought it's going to be useful to sort of separate this out into three basic categories. Okay. And when you approach any paper or experiment or algorithm that someone has developed, you'll be able to categorize it into sort of one of these three categories, and you'll be able to understand, what's the basic idea, and you should be able to understand what foundations apply and where are the foundations being, satisfied, and so on and so forth. Okay, so, from this zoo, let's first extract the theory, and we did some of this theory. Okay, so and there's a lot of theory that can be done when it comes to machine learning. We did some of it, not all of it. We just did some of it. And what did we do? We chose the VC analysis and we chose the bias variance analysis, the bias variance decomposition. Now, these are two particularly, relevant theories to practice, and that's why we chose them. It's not that we couldn't have filled the entire course with theory. We've stopped the theory here because the VC analysis is this fundamental link between E in and E out, and it's this fundamental dichotomy between hypothesis sets into good and bad, and so on and so forth. Okay, and that is absolutely relevant to practice. And if you violate any of the principles that came out of the VC analysis, you will feel the punch when you go to practice. For example, if your data is not IID, you cannot reach from E in to E out. You will fail in the two-step process to machine learning. Specifically, you'll fail in the first step. Okay. If you're learning from one bin and trying to predict in another bin, you will fail. I mean, odds are it's going to be a disaster. If it's not a disaster, you should also be buying lottery tickets. Okay. Now, the bias variance analysis is a specific type of analysis that gives a useful breakdown of the out-of-sample error into two terms, one related to approximation and one related to generalization. So these are two very relevant theories in practice, and that's why we covered them. But there is a lot of theory, and it's not that the other theory is not relevant to practice. Most of it is. It's just that we have a limited amount of bandwidth, and we picked what we think is going to give us the biggest bang for the buck in terms of what we can apply to practice. And this stuff is very relevant to practice. Now you can of course add on. You can put icing on the cake, and there's a variety of, complexity theory related issues in machine learning. There's the Bayesian theory, which sort of starts from the assumption that, you have some prior distribution, over the target function f, okay, and from then on, you go and do things very mathematically rigorously and everything is nice, and it's actually a very beautiful progression of the mathematics to what you can then predict, except that you have this fundamental assumption at the beginning of the Bayesian theory, which said that we have a prior distribution over the target function f. It's kind of like, it's kind of like stealing the bank at the very beginning and then living a righteous life. Okay, that's one way to live, but you still, had to steal the entire bank at the beginning. Okay? And we have maintained a different assumption. Okay? We have maintained the assumption that the target function is unknown. It's completely unknown, and that's a very general assumption. That allows the theory to apply anywhere. You cannot apply the Bayesian analysis anywhere because you need to know this prior over the target function f. You need to know something about the target function f. Okay. There's Rademacher complexities, there's structural risk minimization, and the list goes on. So there is any amount of theory for those of you who are theoretically inclined. Okay. But we will stop at the VC analysis and bias variance theory, and let's talk about techniques. Okay. So there's the theory, the foundations, okay, and then there are techniques. Okay, and we can split the techniques into models and methods. Okay, so let's first talk about models. Okay, and we've spent all of our time essentially on linear models, and it's worth spending time on linear models and getting to know the linear model. It's a very powerful model, especially after you have selected good features. Okay, and there are lots of different models. Neural networks, support vector machines, similarity-based models, Gaussian processes, graphical models, bilinear, singular value decomposition, and so on and so on and so on. Okay. So let me, we'll discuss neural networks, support vector machines, and similarity later, and that's why I've underlined them. So I won't spend too much time there. I will just briefly touch on, some of the other techniques here, some of the other models. Okay, so Gaussian processes, is this approach to regression, which is essentially Bayesian, and it says that you have some prior of your target function, and it's a Gaussian prior, and then that leads to this model called Gaussian processes. Graphical models, similar to sort of are a very powerful learning model, especially in vision. So if you're interested in vision, you might want to look up graphical models. Bilinear / SVD based approaches. When we discussed the Netflix problem, that was one of the solutions that ended up being sort of the winning or the set or a large part of the winning solution to the Netflix prize. So bilinear models. It's not that different from linear models. Okay, so there are lots of different models, and whenever you pick up a paper or you read a textbook or whatever, or you read some approach that someone is using to solve some problem, odds are they'll be using something in this bucket. Okay? And this bucket is also large. Okay? But we are going to focus on, we have already focused on linear, we will focus on neural networks, aka today deep networks. Okay? Support vector machines, which is more robust linear models. So neural networks are cascaded linear models, and then in some sense, the simplest method, the simplest model of all, if you ask, 5-year-olds, how do they do learning, and you show them a fruit and they say it's an apple, and you say, why? Oh, it's because it's similar to, something that was an apple that you showed me, when I was, 4 years old. Okay? So similarity-based models, in some sense, going back to our, our roots, our 5-year-old learning, okay, which is very essentially based on some notion of similarity. Okay. So those are models. Now, methods. So what's different between methods and models? And they both come under techniques. What's different between methods and models is that, models are individual models, but a method is a sort of a higher level concept, a higher level technique that can be applied to all models. Okay? And so here are some examples. Regularization. Okay, so in all of these models, you get overfit. Because what is overfitting? Overfitting is this bad phenomenon that arises when there's noise in the data and you're led astray. And that can happen no matter what your model. It can be linear with nonlinear transform, neural networks, support, anything can overfit. Okay. Now it turns out that, so regularization as a method can be applied to every model. Okay. It turns out that, for example, the support vector machine has some kind of automatic regularization. So just because it's automatically doing it doesn't mean that the method of regularization is not applicable, to that model. Okay. So, validation, again, it's sort of a method that can be used with every model. You can always set aside some data for validation, and then at the end of the day, put it back in and get your final hypothesis that's not deficient. Okay, now, if we have time, we will talk about aggregation, okay, which is a method that is sort of a meta method. It doesn't apply to a single model, but let's say you have run multiple models, and now instead of picking one, which you can do, for example, with validation, you might say, is there a way to aggregate them and get and get one unified model? Okay, so that's the concept of aggregation, of combining different models that you could have used on the data and trying to get the benefits of all of them at the same time. Okay, aggregation. Pre-processing. This is another method. Okay, and we discussed a little bit of pre-processing when we talked about the digits data, where the data has been pre-processed and rotated to a vertical axis and rescaled to fill the 16 by 16 image box. Okay, so that's an example of pre-processing, and we'll talk about pre-processing techniques that can be used. So the pre-processing means something you do to the data before you run your model. Okay, and there are some standard pre-processing techniques that are data-driven pre-processing techniques, as opposed to, for example, those vision-driven pre-processing techniques in the digits data. Okay? And so these data-driven pre-processing techniques, they help the learning. They're not necessary, okay? And you can always learn with a particular model without pre-processing, but typically models are geared in some default mode where they're expecting data of some default type, some default, properties and characteristics. And so if you're going to just take a method and use it off the shelf, then you need to make sure that your data has been put into that default mode. Okay? And so that's basically what pre-processing accomplishes. Okay? And then lastly, so there's the theory of machine learning, there are the techniques which comprises models and methods, and then there are paradigms. And wow, nowadays the paradigms have just exploded. Now, the one we are going to focus on is the supervised paradigm, which is by far the most prevalent paradigm, and it's also the one where you can get the best performance because your data consists of X and examples of F in action. The only case where that's not completely the case is when you're trying to learn a probability, which is logistic regression, where you don't see X and the probability of Y given X, you see X and a realization that was realized according to the probability of y given x. And so that's why we had to develop, some slightly subtle techniques when it came to logistic regression. But by and large, the supervised framework is the most popular framework. It's the most powerful framework, and it's the framework that we have focused on and will continue to focus on in this class. Okay? Now, there's the unsupervised framework, and I showed you an example of this when we talked about unsupervised learning, basically how to organize the data. And we sort of generally have this impression that, organizing the data is a good thing. It can help, the supervised learning, and it is also a useful task on its own. Okay, so we'll touch on unsupervised learning. We may, if we have time, touch reinforcement learning. But okay, and we talked about that. But look at all these other paradigms, and we're not even going to touch these other paradigms. Okay, so active learning. Okay, so we have assumed that the data comes to you IID. Okay, according to some data generation process. Active learning says, I can have some role in choosing the data. So as you're collecting data, I can do learning, and then I can identify, I'd like to get that data point. So you go and sample that data point and figure out what F is on that data point. Well, okay, you should probably see the problems with this or the challenges with this paradigm, because what about E into E out? E into E out, assume that the data is IID. So you have to deal with that. Okay, you have to deal with the fact that the data is not coming IID. So on the one hand, it might help you because, you can think of it this way. I'm going to actively select data on which would improve my understanding of the problem the most, which would get me closest to the target function. So you can think of it operationally as follows. I have learned something, okay, but my hypothesis that I have learned currently is very uncertain in this region. So let me get some data there to nail it down. And as I nail it down in all the various regions, I'm now very rapidly approaching F. Except that, we've lost the E into E out maybe because we're not doing IID sampling. So it's a little bit sophisticated. It's a little bit challenging to figure out, how to analyze various active learning scenarios where the learner can choose data points. Reinforcement learning has an element of active learning, because in reinforcement learning you get to choose what to do next in your life, and depending on what you choose to do, then you get some feedback. And so you're at the same time learning, you're choosing the data point that you will see, and then the environment is rewarding you or penalizing you. Okay, so reinforcement learning is very complicated because it can be a blend of many of these paradigms. Okay, the online learning paradigm, again, the online learning paradigm is also present in reinforcement learning. So what's the online learning paradigm? You have to learn as you get the data, and you would like to learn quickly, and usually you can't store the data. Okay, so you learn because the data is coming at you at such a rapid rate that you don't have the capability to store the data. So you get data, you learn, and then you act, and then you move on, and then you get new data, and you learn, and you act, and you move on. So that's the online paradigm. And reinforcement learning, especially the learning that humans do, has a flavor of online learning. Unlabeled data. So we've assumed that all the data is labeled, supervised. Okay, and in the unsupervised scenario, all the data is unlabeled, and the only task is to organize the data. But what about if you're in the supervised framework, where the goal is to predict, okay, not organize, the goal is to predict, and you have some data that's unlabeled, and you have a lot of labeled data. How can you use the unlabeled data to help the overall learning process? And you can think about this in the following way. The unlabeled data sort of tells you about the distribution P of X. Okay? And why is the distribution P of X relevant, or a more accurate estimate of the distribution P of X is more relevant? Because it tells you where you are likely to be tested out of sample. So you can focus your learning, more in a more precise way on where you are likely to be tested. Okay? And the unlabeled data usually is very numerous, and so it really pins down the distribution P of X, which has two roles. The distribution P of X that generates data has two roles. It generates the data, but it's also, it's also responsible for generating the test point, which sort of, in some sense, you can think of as weighting the data space according to which, areas are high probability and likely to be the source of the test point. Okay? And so knowing P of X should be able to make your supervised learning task much easier. Well, that's just one way in which unlabeled data can help you. Another way is it can regularize, and so on and so forth. Okay. Transfer learning. Okay, I put it down here, way down there, because it wasn't a big deal some time ago, but now it's a big deal because transfer learning is a very significant part of, at least today in the big applications, how deep networks are trained. Okay. So for example, a deep vision network is trained on a huge image database, okay? And now you come and try to fine tune it, okay, for your specific application. So you're transferring knowledge from the huge image database to your specific application. So that's transfer learning. Okay. Think about it this way. I've learned how to drive a car. Okay. And now I need to learn how to drive a truck. Isn't it going to be easier to learn how to drive a truck now that I know how to drive a car? I can transfer a lot of the learning that I did in learning how to drive a car to helping me to learn how to drive a truck, and hence I will be able to learn how to drive a truck much more quickly using much fewer data points, as opposed to if the very first thing I tried to do was learn how to drive a truck, okay, from scratch. It would take me a very long time. But knowing how to drive a car, I can transfer some of that learning to learning how to drive a truck. Okay. That's the essence of transfer learning. It's one of the ways in which you can sort of make learning with very deep, very huge million parameter neural networks tractable. Because otherwise, there's just way too much complexity in the neural network. So what you do, you nail down most of those parameters in some huge unrelated database, and then come and fine tune on your actual problem. Big data, nowadays big data, big buzzword also. Okay, lots of data being thrown at lots of various machine learning applications. Okay, now. I don't mean big data as in lots of data is available. I mean big data as in, for example, think back to when we did our algorithms. Let's say we're doing a neural network algorithm or a linear algorithm, so the perceptron learning algorithm or the logistic regression with gradient descent. The cost of one iteration is sort of, ND. Okay? And then if you do SGD, you still have, order of D. And if you're in a million dimensions, one iteration is very costly. So what the realm of big data says is, your data is so big, okay, that if you could learn on all the data, you would output the final hypothesis G. Okay. But now it's such huge data that you cannot learn on all the data. So is there something you can do to output a final hypothesis that's close to G? In other words, your target function has effectively become G, but because you can't process all the data, what can you do to get as close to G as possible? For example, can you downsample the data in smart ways so that the final hypothesis that you output is close to the final hypothesis that would have been output had you been able to learn on all the data? And big data comes into view when the had you been able to learn on all the data becomes impossible. That's what we mean by big data. Not just that you have lots of data. Big data really means that, it's just too much data to learn from. Okay? But we'd like to learn from it. So how do we do it efficiently and get to the same approximate solution? Okay, so theory. We've done some theory. Techniques. Okay. Fall into models and methods, and we've done linear, regularization, and validation as methods, and linear as model. We'll now talk about other models, and for all these other models, we'll have to discuss overfitting and the two-step process and E-in versus E-out and so on and so forth. So that's what I meant by the foundations are going to be with us no matter what techniques we discuss. Advanced, simple, whatever. Okay. And paradigms, well, unfortunately, we could teach an entire course on each of these paradigms, but let's not do that. Let's just focus on supervised for the moment. We'll touch unsupervised, okay, and maybe we'll touch reinforcement. Okay. So, moving forward. So we've done our foundations, modules 1 through 5, and so we're going to discuss advanced techniques. We're going to start with similarity, as I said, the 5-year-old's approach to supervised learning. Then we'll talk about neural networks, this big buzz thing today. Deep networks. They used to be just called neural networks. Now they're deep networks. Okay. We'll even see a theorem in neural networks that basically says you don't need deep networks, but people like to use them. So, okay, so that's nice. We'll talk about support vector machines. So neural networks are cascaded linear models. Support vector machines are more robust linear models. So you see linear models everywhere. Get to know the linear model. Okay. And then we'll talk about pre-processing, and maybe we'll talk a little bit about aggregation. In terms of other paradigms, our plan is to, spend maybe a lecture on unsupervised learning, a very small amount of unsupervised learning. Believe me, there are entire courses, entire years taught on unsupervised learning because there's the formulation of the problem, there's efficient algorithms, there's various different applications. Okay, and we'll maybe touch reinforcement, and it's reinforcement is kind of shaded light gray because if we do touch, it's definitely not going to do it justice. Okay, and so that's all for today. And we'll see you next lecture where we will start with the advanced techniques, and in particular we will be talking about similarity-based methods. Okay, so modules 1 through 5 have basically covered the book. Okay, the first 5 chapters of the book, which is hopefully going to be your friend for the rest of your life, for the rest of your machine learning career. Okay, and all all the material for the remaining techniques that we're going to study are all available as e-chapters to the book, okay, on the book forum. Now, why e-chapters? Because the foundations are never going to change, and they're worthy of being put in a book. But the advanced techniques change from time to time. Some become more popular than others, and the e-chapter allows for a more dynamic updating process. And so access the e-chapters and start reading the similarity-based models, which is e-chapter 6 on the forum. Okay, and see you next time.